So if the Poynting vector is constantly varying based upon the constantly varying electric and the magnetic fields, or we can work out what the maximum of the Poynting vector is, you might be wondering, how are these terms useful? Well, what is a useful term to work out is the average energy transferred through a surface area over time. We would call this the time averaged value of the Poynting vector over one cycle, and we label this intensity. So this is what we call the intensity of an electromagnetic wave. So the way that we can work this out is by using our equations for the electric and the magnetic fields that we found last lecture. So remember our wave equations, and we worked out that the solutions to those wave equations are going to be what we've seen before. So for the electric field, it's our E equals max of E cos kx minus omega t, and the same thing with the B field. So let's actually sub these in to our Poynting vector equation and see what we end up with. So remember, the Poynting vector is S equals E times B divided by mu naught. So then let's sub in our values. So when we do that, we get E cos kx minus omega t, B cos kx minus omega t divided by mu naught. So then we end up with E max, B max, cos squared kx minus omega t divided by mu naught. So the question now becomes, what is the time averaged value of cos squared kx minus omega t? Well, this is actually 1/2. So when we sub that in, we end up with S equals E max B max divided by 2 mu naught. So if we wanted it in terms of E, like we said before, it would be E max squared divided by 2 mu naught C. Or if we wanted it in terms of the max of the magnetic field, we would say C multiplied by B max squared divided by 2 mu naught. So this is the intensity of the wave. Now, remembering for point sources where the radiation radiates isotropically, that would mean that the power generated by that source is going to reduce by 1 over 4 pi r squared, where r is the distance from that source. Now, why is it 4 pi r squared? Well, 4 pi r squared is the surface area of a sphere. And remember what we covered last lecture is that for a point source, it radiates out the same in all directions, which means we end up having a spherical wave. One example that we can think of for this type of thing would be a star. So a star in the night sky, it has some given power in watts, and it is producing energy at that given power. But as we get further and further away from the star, some distance r, for example, the intensity is going to drop. So we can have a star that is really close or a star that's really far. The intensity is going to be a lot higher when that star is closer to us. We can also think about radiant intensity, which is going to be the power in watts per solid angle, but we don't cover that much in this course. Another useful way that we can describe the electric and the magnetic fields is using what we call the RMS values, or the root mean square values. Now, the root mean square in general is basically a way to describe the magnitude of time varying variables. So for example, it's used a lot in electrical engineering when you're talking about AC versus DC current. So what we do is we take what we call the root mean square of the maximum of a value. So for example, for our maximum of our electric and magnetic fields, the root mean square of each of those would be E RMS equals E max divided by square root of 2, or for the magnetic field, it would be B RMS equals B max divided by square root of 2. Now, the whole point with an RMS value is to kind of work out what the scalar equivalent is. Like I said before, it's used in electrical engineering. So for AC and DC currents, if you took the RMS value of an AC current, what you would be doing is essentially working out what the DC equivalent of that AC current is. Same thing with When we're talking about molecular speeds of gases, you might remember that from Physics 1A, you can find the RMS speed of particles in a gas. And what that essentially does is, we know for velocities that you have, two particles going in opposite directions with equal velocities. Their average velocity is 0, but that's not representative of how fast they're going. So in that case, we would take the RMS speed of those particles. And the cool thing with RMS is that slots directly as well into our equation using the speed of light. C equals E divided by B. So we can say C equals E RMS divided by B RMS.